All right, hello everyone. Hope you're all doing well. We're going to continue our conversation on functions, this time talking about the domain of those functions. Now, we kind of talked really briefly a little bit about the domain as we went through yesterday, but we're going to kind of go a little bit more in depth today. Basically, the domain are all the possible inputs you can put into your function. We also a lot of times refer to them as the x's. The x values, because those are our inputs that we usually put in. Okay, so it's the inputs, the x values, the domain, those are all interchangeable. What can you put in your function? And we're going to see as we go that can really change a lot from function to function. Sometimes there are functions where certain numbers we cannot put in, and other times we can put any number we want to in. We want to be able to say that. Okay, there are going to be a couple sets of numbers we're going to see from time to time that will show up in terms of the domain. The first one would be all real numbers. Oh, it is not letting me write. Okay, so the first one would be, let me put on my pen here. The first one would be the real numbers, okay, otherwise known as this kind of italicized R, okay, and you'll see me write that from time to time as we go through, or all real numbers, we'll call it a lot. We'll see that a lot, okay. That's kind of the most common one that we'll see from time to time for the domain is the real numbers. The next one's represented by the Z. That actually are your integers. Okay, yes, I know you're probably like, Mr. Guy, why the heck are they using a Z for integers? That's because I is already being used for something else. And apparently somebody one day misspelled integers and put a Z on the end. And so they decided that that would be the most appropriate letter for that. Okay, but whatever it is, the integer is what we use for Z. And then N would be the natural numbers, and we'll see this from time to time as our domain values, meaning that those are the only numbers you can plug into that function. So, all right, so we talked about domain. What are some examples of what am I going to have to do with domain? So basically what you're going to have to do is look at these functions and then say, all right, well, this is the domain of this function. This is what I'm allowed to put into the function that will work out. So for example, x squared plus 3x plus 5 is going to have a domain of x is a member of the real numbers. Okay, so this little e thing means a member of, and this r with a double italicized we saw in the last one is real numbers. Basically what that means is I can put any number you can think of into that function, and I'm going to get a real number out. I'm going to get a value out. And we're actually going to see that for all polynomials, our domain is going to be all real numbers. There really are nothing that's going to cause a problem or nothing that's going to restrict what I can put in, no restrictions on my domain. Where we are going to start having a problem is with rational functions and radical functions, because if you think about what are the problems we have in algebra, dividing by 0 and square roots and negatives tend to be the biggest ones we have so far. That kind of takes us into the no solution space, which is where we're going to have these domain values that don't give us range values or y values and that we can't use. So for example, this function right here, g of x, I would say I would have a domain, and I'm going to use what's called interval notation, from negative infinity to 6, and then I put a u in between, which means union from 6 to infinity. Oh, I don't know why I did that. All right, little technical difficulties for a second there, but I went ahead and fixed it. So I have this negative infinity to 6, and then the u means union, 6 to infinity. Basically what I'm saying is that it's from the interval of negative infinity to infinity, but 6 isn't included. Another way we could write this is that we could say, hey, x is a member of the real numbers, except that x cannot equal 6. Okay, that's another way we can write it. X is a member of the real numbers, but x can't equal 6, all right? And the reason why we're saying that is because if I put 6 into this function, I'm going to divide by 0, and that causes a problem, okay? So we're trying to avoid that division by 0, which causes a problem. So we're saying, hey, you can put anything you want into this equation except 6. When you put in 6, we have an issue, okay? Same thing with square roots and negatives. We want to try to avoid those. Square roots and negatives also cause problems for us. So the way we're going to do that is by looking at this and saying, all right, well, what kind of numbers can I plug in here that'll work that are not dividing by, or not the square root of a negative? And basically what that means is that x would have to be greater than 4. Okay, so x had to be greater or equal to 4. And the way I would show that here is using the intervals, I would put a bracket from 4 to infinity. So what we're saying is that x can be anything from 4 to infinity, and we're good to go. All right, if I have anything less than 4, let's say I had 3, I would get a negative number underneath that square root, and I would have a problem. So that's really what we're looking for with domain. I always say you want to just ask yourself, is there anything in this equation that will cause me an issue? It's basically, is there going to be any division by 0, or is there going to be any negative underneath my square roots? Piecewise functions are functions that are made up of different portions. Basically, over different parts of the domain, we're going to have a different rule. So, for example, this could be a piecewise function here. And what I'm saying with this function is that anything less than 0, I put into the top function. Anything greater than or equal to 0 goes into the bottom function rule. And that's what kind of makes up this function f of x. So if I put in -1, that would go into the top function. So I would have f of -1, and for that one I would plug it in the top and say, all right, -1 squared plus 1, which would equal 2. The bottom one for 0 would go into the bottom equation because that's where it says on that domain I use this rule here, so that means that f of 0 would equal -1. Okay, so basically for a piecewise function, there's two different rules, and they all kind of interchange based on the domain I'm on. If I'm for this one, less than 0, I use the top rule. Greater than or equal to 0, I use the bottom rule. They'll all kind of tell you what domain you use the rule on. You just plug into where you're supposed to plug into, and that's all you have to do for a piecewise function. Okay, we're going to skip ahead and talk about this application of the difference quotient. This is actually a little bit of a calculus application for what we were talking about, but it's kind of something cool that sort of happens with us when we go and try to use or think about our functions. Okay, so here's what I want you all to do. I want you to go ahead and look at this function up here, and I want you to apply this to this function down here. So it says the value of the function x squared minus 4x plus 7. Basically, what I want you to do is everywhere you see f of x of something, put that into this equation. So for example, f of x plus h for this, I would say, all right, well, that's going to be x plus h squared minus 4 times x plus h plus 7. And then I'd say, all right, minus, and then here it would be, okay, f of x, so that would be minus x squared minus 4x plus 7. And notice how, because I'm subtracting all of f of x, I put this in parentheses, I'll have to distribute this negative through. And all of that's going to be over h, which I think we're going to have the technical difficulties again. But this whole thing is going to be over h, all right? And that's the whole thing. So that includes this, all of this over here. All of it's over h. What I want you to do is I want you to go ahead and evaluate this, okay? I want you to simplify this. I want you to do x plus h squared. FOIL that out, okay? Distribute this -4 through. Distribute the negative through here. Combine like terms. See if anything will simplify or cancel, okay? Go ahead and do that, and then I want you to see what you end up with, and we're going to have a little bit of a discussion about what this means and what we kind of saw here. So go ahead and do that, and we'll talk about what we got. All right, so hopefully you went through and simplified that all, and what you end up with is 2x minus 4 plus h. So if you FOIL this out and you cancel things out, you should eventually notice that you have an h with all your terms. You can cancel your h's out, and you end up with this expression right here. Now, Mr. Guy, what was the point of that? What did we just do? Well, this is what's called the difference quotient, which if you could read, you probably already knew. So what's the difference quotient? What is it saying? This is basically showing us the distance or the difference between two different things, okay? So basically, depending on how large of a gap between 2 points I want, I can figure out the difference between them, all right? So if I had an input, I wanted to figure out how far away, or h away, from this one over here, I can figure out the difference by using this equation, how far away they are. So let's say we had a curve like this, and I had a point here, and I had a point here, and I wanted to find the difference between them. This equation would tell me the average distance, right? So I would say, all right, well, it's the difference between these points. I can go ahead and find that using this equation. All right. Well, what's really cool about this equation, what's really cool about what we just did, is this actually is kind of an introduction to some of the things you'll talk about when you're a junior or senior and you take calculus. Because in calculus, it's all about the measurement of really, really, really small things. What if we had a difference of basically zero, an instantaneous thing that we were trying to get? So one thing that's really valuable for us to find is slope, right? And slope actually is calculated by using a version of this difference quotient, okay? What's the slope of different lines? And we pick 2 points and we find the slope. Well, with curves, to find this slope, it's a little bit harder. What I just found here is what we call a secant line where it touches twice, okay? Now, what we want to actually find is something called the slope of a tangent line, which is a line that touches a curve only at 1 point. The problem with only 1 point is that the difference between the 2 points is literally zero. Okay, there is no difference between the points, it's the same point. How do I calculate a slope when I only have 1 point? Think about when you calculated slope before, you always needed 2 points. We can't do it with 1 point. So in calculus, what you say is all right, what if I did this difference quotient, but I said that h was zero, the difference was zero? When I look at the original function, that would cause me a problem, right? Dividing by zero, you can't do it. The world explodes. Everybody's going to go crazy. We can't divide by zero. But what's cool is that you guys just saw by simplifying, the h in the denominator actually cancels out, and we end up with this equation that represents all of those slopes for us. So I could go to any point on my curve here, and I could actually find what the slope of a line that touched it at that only point would be. And that's actually really powerful and really cool, right? Think about your car for a moment, right? Normally when we calculate speed, we need 2 different points in order to calculate that speed. It's the average distance you're covering over time. Well, when you're in the car tells you the exact speed you're going at a single time. Is it constantly calculating all the different points? No, it's actually using this idea, using calculus to say, what's the speed at this instant moment? What's the speed right at this time? All right, and it's using this difference quotient that we saw here. All right. Main application, I want you guys to be able to do this simplification and be able to get to this answer that I have here. But what's kind of the bigger brainy concept going on here? It's that idea of, oh, what if I want to find an instantaneous speed or an instantaneous difference? How do I do that? All right. Thank you all for watching, and I hope you have a nice day.